Hi, y'all. It's Ms. Blasky. Today I'm going to jump around in your packet a little bit. We're going to talk about topics 8.4 and 8.6. I think they go together pretty well, and so I'm just going to smush them together. We'll come back to 8.5 in the next video. So today we're going to talk about this thing called Hess's Law. So again, this is something that hopefully you vaguely remember from Gen Chem. Hess's law tells us about how we can combine different pieces of information to find out the overall change in enthalpy, or delta H, for a chemical reaction. So the first way we're going to talk about in topic 8.4 is about talking about when we already know the heats or the enthalpies for different chemical reactions. So for example, if I want to think about the complete combustion of ethanol, there's a couple different ways I can think about this. We could think about the standard enthalpies of formation for each of the substances in this chemical reaction. So notice we talked about what the heat of formation was last time, or enthalpy of formation, what that little F was, right? We said enthalpy of formation comes from how much energy is either released or required to make that substance from its elements. So lots of times this is information that's in big tables. You can look this up in books or on the internet. But that little zero up at the top, this means standard. So just like we had standard temperature and pressure when we talked about gases, we have standard enthalpies, which is not exactly the same standard as when we talked about gases. Of course, that would be way too easy, right? So when we're talking about standard enthalpies, we're talking about pretty much sitting on the counter in a room. So 25 degrees Celsius, which is pretty close to what's considered room temperature, and 1 atmosphere of pressure. So we could talk about how much energy it takes to form liquid propane from carbon, hydrogen, and oxygen, how much it takes to form carbon dioxide from carbon and oxygen, how much energy it takes to form water, liquid water particularly, from hydrogen and oxygen, because it takes a different amount of energy to form a gaseous water from its elements. But oxygen is in here by itself. Oxygen as a gas is what it exists in standard form, right? If I'm sitting in a room at 25 degrees Celsius and 1 atmosphere of pressure, oxygen is already a gas. It's not formed from its constituents. It is a constituent. So its enthalpy of formation is 0. So we don't need to worry about that one so much when we see an individual element at its standard state. Now, we can use those individual heats of formation. We'll talk about that in a second. Or just like when we were in kinetics, we can talk about how we can make certain steps combine together to make an overall equation. So for example, if I can, maybe it's too difficult to find the overall heat of the reaction for this combustion reaction. Maybe there's too much going on. Maybe it happens too fast, all these sorts of different things. I can find the heat of reaction of other different steps or other different reactions, and then I can combine the heats of reactions of those steps together to get the overall heat of reaction for my combustion. So for example, here I've got the heat of formation of my my ethanol. I had to remember what chemical I was talking about. But this is reversed, right? So heat of formation is usually taking the carbon, the hydrogen, and the oxygen and combining it to form that ethanol. But this time we're actually taking this reaction and flipping it because I want that ethanol to be a reactant. So the heat for this whole reaction, or the delta H for this reaction, is the inverse of my heat of formation for this reaction. So by flipping that equation, I have flipped the sign of my delta H. And then I've got an equation for the heat of formation of carbon dioxide. the carbon plus the oxygen makes the carbon dioxide. But notice that this has got all of those chemicals now have a coefficient of 2. 2 carbons plus 2 oxygens makes 2 carbon dioxides because I need 2 carbon dioxides in my overall equation. So this is the equation for the heat of formation. I am forming that carbon dioxide from my elements, but I doubled it, which means I'm also going to double my delta H value. And then for my last step, normally this reaction would be H2 plus half an O2 makes 1 water, but in order to get the 3 water molecules that I need, all of these coefficients were multiplied by 3. So the heat of formation of water from hydrogen and oxygen is going to get multiplied by 3 so that I can get the correct formula out for my overall balanced equation. So this is doing exactly what we did in kinetics when we needed to combine those steps to get my overall equation. So to get my overall heat of reaction, I take each one of the delta H's for those 3 steps, I add them together, and overall I get that my heat of this combustion reaction is negative 1362 kilojoules. Right. So let's try out this process on our own where maybe we have to manipulate some of these equations ourselves. So let's take a look at equation 19 or example number 19. So here's the equation I want to get to. N2 plus 2 O2s makes 2 NO2s. The equations that I have available to me are the heat of formation of nitrogen monoxide, but I want nitrogen dioxide. And then the decomposition reaction for nitrogen dioxide. So let's see, how can I manipulate these equations to get them in the order that I need them to be? Well, I need NO2 to be a product. So I want to take this second reaction and I want to flip it around the other way because that would make NO2 be a product instead of a reactant. So I'm going to have 2NO plus O2 makes 2NO2. So by reversing that reaction, I've changed my delta H for that reaction now to be negative 112 kilojoules, because by reversing the reaction, I reversed the sign on my delta H. It's now an exothermic reaction instead of an endothermic reaction. If I add together that with my first reaction, N2 plus O2 makes 2NO. Let's see. 2 NOs and 2 NOs are going to cancel each other out. So that's going to give me a total of N2 plus, I've got 2 oxygens now, makes 2 NO2. That matches up with the overall balanced equation that I need to get to. So now all I need to do is I need to combine my delta H's for those 2 steps, accounting for any of the changes that I made. So the first step is still going to be positive 180 kilojoules because I didn't manipulate that equation at all. Second equation, I just flipped it. So now that's going to be minus 112 kilojoules. So overall, my delta H, the reaction, is a positive 68 kilojoules by combining those 2 steps to get the delta H for my overall reaction. Right? So we can do that. Sometimes we're going to have multiple steps that we have to add together. Sometimes we might have to change some coefficients like we saw earlier in order to get the correct number of reactants or products that we need for our overall equation. So this is one way that that information can be given to us. Let's go ahead and jump to section 8.6 to see how that works as well. So in 8.6, we're going to be thinking about the same ideas. We're going to be thinking about that delta H of the reaction, but we're going to be given different data. So instead of being given data for whole reactions and having to combine them, we're going to be given just the heats of formation of individual chemicals. So in order to find the overall heat of reaction or enthalpy of reaction, we're going to add up all of the heats of formation of all of the products and then subtract the heats of formation of all of the reactants. Now, again, we need to remember that the heat of formation of anything that's in its elemental form is going to be 0. And so that's probably not data they're even going to give you. So don't freak out if they're not giving you that particular number. We just need to remember that that's going to stay 0. So there's really no sort of background to this. You just sort of dive right into the math. Example number 39 says, determine the standard enthalpy of reaction for the combustion of hydrogen sulfide gas. We've got the equation below, and then they give us this little table of standard enthalpies. So I know that my heat of reaction, this is going to be standard because everything that they're giving me is standard, so I put that little 0 in there. So I need to, my products in this case are water and SO2. And they have coefficients in front of them, right? I have 2 water molecules and 2 sulfur dioxides. So those are all of my products. And then I need to subtract away my reactants. So I've got 2 hydrogen sulfides, and then I've got 3 waters, but those waters, remember, are going to be, a heat of formation is going to be 0. So when I do my math, I have 2 waters. Now we need to make sure that we're being very careful about states of matter. Sometimes they might give you some extra data that you don't need to use. They might give you both H2O liquid and H2O gas to see if you're paying attention. So I have water as a liquid, so I need the heat of formation for liquid water. And I'm going to multiply that by 2 because notice that this is kilojoules per mole. I have 2 moles of water. So 2 times negative 285.8 plus 2 sulfur dioxides, which is negative 296.8, minus 2 hydrogen sulfides, which are gases, which is negative 20 each, and then oxygen is 0. Now, you need to be very careful when you do this on your calculator. It might even be nice to break this up into some steps, just because of all of the positive and negative signs, things can get screwy pretty quickly. So I'm going to take 2 times negative 285.8 plus 2 times negative 296.8. Oh, those numbers are pretty close to each other. So that gives me an overall number of negative 1165.2, and then minus negative 40 means that I'm adding 40. So overall, my delta H of this reaction is negative 1125.2 kilojoules per, not per mole, sorry, kilojoules. I don't write the per mole because I multiplied them up, because I basically took 2 moles times the kilojoules per mole. So all I'm left with is kilojoules. So that's pretty straightforward. That's just a plug and chug, but you need to remember that it's always products minus reactants. This is information that is not always given to you on questions. I believe that I don't have an equation sheet in front of me, but I'm pretty sure that that is on the back of your equation sheet. I think they give you the delta H, the delta G, and the delta S, which are all variables we will be talking about this unit. Right. So there's a couple more example problems, so we're trying all these out. Here's some tables where they give you some extra information where you need to think about what information do I actually need to pay attention to on that chart for the particular problem I am solving for. Right. So we will keep practicing this in class, and I will see you all later. Bye.